Okay, thank you. So I think we start with whatever is remaining, because last time we discussed about Kafka workflows, and also we discussed the role of zookeeper. Okay, so this time we will discuss Kafka's controller broker, and then delivery semantics, and maybe the characteristics of Kafka in a very brief. Okay, so now what is a controller broker? So what it says is, in Kafka, as we all know, if we go to this previous diagram, and here, so we usually have like all these brokers, they form a cluster, and all these brokers are stateless, and so they actually uh, get uh, get requests from producers, and they publish the messages from the producers, and they're consumed by the subscribers or the consumers. So they are stateless, and they all have the same responsibilities. That is what we discussed earlier. But in this case, for what happens is, for the controller broker, it is nothing but the same brokers what we have in a cluster. So one of the broker in a cluster will become a controller, and the way it becomes, so what the definition says is, it's just a normal broker that simply has an additional responsibility. Okay, so the way a particular broker is selected as a controller, imagine if like your cluster is just starting up, if there is none of the brokers are on, and they start one by one. So whenever any broker, it comes and registers to the slash controller z node in that zookeeper and symbol, so that broker will be your controller. So as simple as that. So whichever comes first, and whichever registers first to that controller node, will be the controller broker, and that is the way it starts. And then how actually it is it moves the responsibility from one broker to another, that we'll discuss later. But also any broker, and that is what is very clear, right? So any broker can be a controller broker. It's not only it is very specific, or it has to have a very specific configurations, not like that. Any broker can become. And the responsibilities that a controller broker are they are mostly administrative actions. And we also saw in the APIs that there's an admin API. Okay, so if I go back here quickly, so in that case, so it will have this admin API. So this is the last API what we were discussing earlier. So this admin API is all related with the with this control broker. So what are those administrative actions which a controller perform? The first is like it can create and delete a topic, and also it can add partitions. And so when it add partitions, it can assign them the leadership. So whichever partition has to become a leader, that also is the responsibility of the controller. And also it deals with the situation when the broker wants to leave the cluster and all that stuff. So again, the same thing with the cluster broker management. So it means that whenever a new broker is added, so it actually takes the control of that, how it is assigned and all that stuff. So if any broker is shutting down, what we were discussing here, or if a broker fails, okay, so that all cluster broker management is done by the controller. And it also does a preferred leader election. Okay, so there is something called as preferred leader election. We'll come to that. And the other is the partition reallocation. So partition reallocation is something like a rebalancing of the partitions. If the partitions which are already present have be loaded in a different way, and they are not the best way, because it's being overloading more some of the brokers, and some brokers are not so much loaded. So there is some way to reallocate that, but that I think we have already discussed, so we won't go in details now. Just to give an illustrative example of how what happens when a broker is leaving a cluster. So this is one diagram I just got from some blog, and it shows here we have zookeeper, and there are about these 5 brokers over here. And if you see, the blue ones, the blue partitions, they are the leaders, and the orange ones are the followers. So like we have these 5 of them, and so here currently the controller is a broker 3. Okay, so now if we imagine a scenario when a broker 2 goes down, so how does a broker 2 go down, and so what happens actually? So if a broker 2 goes down, because we all know that every broker is sending a heartbeat to zookeeper. So usually every broker will have their z node and symbol created for this particular broker in the zookeeper z node, and that is the ephemeral node, right? So whenever this broker 2, for some reasons, like it's a GC pause or some transient response, or so delays for the heartbeat, so then that session will be terminated. And when that session is terminated, so the controller broker will be notified. And how it is notified? So what will happen is this zookeeper will have a watch on all these broker sessions, and that watch actually will be an input to the controller, and the zookeeper's watch will inform the controller broker, which is the currently broker 3, that broker 2 has gone down, and then he needs to take an action. So in this case, what he does is he first goes and looks for the broker 2, how many leaders this broker 2 has. In this case, there were partition 2 and partition 3 were the leaders. So we don't want to lose these leaders, because what will happen if we lose the leaders, and we all know that any of the publishers or the consumers, they actually read and write from the leader, isn't it? So we'll have a slight some sort of inconsistency during that period, right? So that is the reason it has to take immediate action. And now in this case, in this scenario, what they have shown is they have elected the partition 2. They have made the broker 4's partition 2 as a leader, and the broker 5, the partition 3 in this case becomes a leader, and in broker 1, the partition and 2 and 3, they are made followers, and then this broker 2 actually goes away. Okay, but now what happens in some cases, this broker 2 has not gone for long, or it's like almost it is a transient failure because of the GC pause, and then it comes back again after a certain time. Okay, so what it talks about here in this scenario is like this is something like a preferred leader election. So what does this mean is, whenever this broker 2 comes in, and before even the broker 2 goes down, so if you look at the whole of these um, cluster, so the way the partitions were assigned, that was the most optimal way to assign the partitions. That is why it is, because it was rebalanced and everything. And so that rebalance was automatically done if based on the feature, if it's that feature is enabled. So the cluster is completely well balanced. So if a broker 2 goes down, and the way the controller assigns the partition based on the current availability, it might happen that it imbalances the partition load. Okay, so therefore, whenever the broker 2 just comes back again, okay, in that case, because that broker 2 had partition 2 and partition 3, which were the preferred leader. So this information is also stored somewhere in the zookeeper. And then when this particular broker comes back again, broker 3 knows that these are 2 and 3 leader, which are recently were reassigned to some other broker, like broker 4 and 5. They were not a good one, but if I get back the broker 2 again, then it is always better to revert these leaders or partitions back to broker 2. And that is what they call something what is said here as preferred leader election. And then the broker 2 becomes a gets its status back, and whatever the leader partition, whatever we were actually assigned before, they will be reverted back by the controller. So this is also a very important function or feature what controller does. And if you really understand now, the controller broker is the very important broker service. It is just like a service, I think, but any broker can be a controller. Okay, any questions so far?
There is question in chat. I think Nick has asked, right?
Yeah,
Like,
please go ahead. Yeah.
how does controller decide which one broker should be a leader for a particular partition?
Oh,
So the whichever partition has latest data, right, or a high watermark, something like that, right? That
yeah,
should be
the
the next.
Insync replicas, actually, based on the Insync replicas, they decided. Yeah. So yeah, so whatever you can say, in the high watermark is for the consumers, and basically the Insync replicas will be those list of replicas which are preferred leaders. Okay, so those will be all the brokers in that the partitions in that particular list. So based on the Insync replica list, it will elect the leader.
Okay, so I mean the data up to which has been read in all the three, right?
Yeah. So
To which
the way we had discussed last time about Insync replicas, it maintains a list. It looks for whenever a leader is there, and it looks for other followers and see whichever follower is catching up with the leader. So there is some time configuration time for it also. Every time, because it whenever a message is published to a leader, the followers actually, the leader really doesn't go and push that message to the follower, but the follower has to request to the leader, and that is a pull based way of actually replicating. So whenever follower actually request for updating from the leader, and it updates based on within that stipulated time or the number of messages, so that particular partition in that other broker is also considered to be a part of the Insync replica. And so that is the way, if the leader fails, then the other followers which are in that Insync replica list will be elected as a leader.
next leader.
Yeah. Hope that is a question answered. Okay. So now this will happen. A split brain might happen in this scenario, isn't it? So what is a split brain? And it's the same thing what we might have discussed in the DDIA. So now in this case, if you imagine this is Zookeeper and we have just 3 brokers, and this broker 3 is a controller, and then for some reasons our broker 3 goes down. Okay, so and so what will happen is, it will actually, because that was configured in this slash controller in this Zookeeper, so at that particular path, so this session will be terminated. So now it is like every broker will actually try to go and again write to this controller. So they will try to acquire that, so to become a controller. But here in this case, if you look, controller 2 was successful in it. So then the the broker 2 was successful to become a controller, and then it will notify all other brokers by that watch again. From the Zookeeper, it will be notified to all the brokers. So broker 1 knows about it, but broker 3 is still down, and it is till the broker 2 has become a controller, there was no action for broker 3. It was almost dead for that time. So broker 1 and broker 2 both know, broker 1 knows that broker 2 is the controller, and then they go on. But suddenly after some time, this broker 3 also comes back, so then this broker also will start sending all the admin commands to other brokers. So then there will be a split brain issue. And how this is resolved is by the mechanism called as a generation clock, right? So generation clock is nothing but, it is something called as epoch number, right? So if you look here, this is very small diagram, but here it is written slash controller dash epoch. So that is the path. Okay, so in this path slash controller that epoch, which is in the Zookeeper one of this node. So the value here, whatever the value is there, which will be all the latest one. So whenever one broker dies, or the first time a broker is assigned its controllership, so the value may, if it was 1, so next time whenever the second broker becomes a controller, in this case broker 2, so that value will be updated. So whenever any of these controller brokers, they send the admin messages, they always send this epoch value also. And that is the reason that helps for the follower brokers, which are not the controllers. Whenever they get these admin messages, they will look for that epoch value, and whichever whichever message has a greater epoch value will be considered, and that is the way they resolve this conflict. Okay, so this is the way
This value is get assigned through some centralized server, right? This epoch value.
Yeah, so whenever this is actually in Zookeeper, this value, and initially whenever the controller comes in, so it will have that slash controller path. In that it will have a slash controller epoch value also. So whenever a broker is assuming or maybe taking the position of as a controller, it will update that value. So it will just increment the previous value.
Okay, got it.
And then you will have a watch on all of these from this Zookeeper watch for whichever broker want to subscribe. So they will come to know what is the new value also. Yeah.
And when new one is come, try to claim as a master, right? And he has the epoch value 1, so that's why it is lower than the existing one. That's why it is not take the ownership. I mean, take the master role, right?
Yeah, so it will still send, but in that case, the epoch value will be 1, right? The previous value. So therefore, those messages will be rejected. And eventually, I think because in this case, the broker 1 rejects that epoch value 1 message, but eventually then the broker 3 will understand, because its messages are not being accepted, then it might stop sending messages. That is what I assume. It was not very detailed in that, but they just said if it's a higher value, the broker 1 will only always consume the higher values and ignore the lower ones. But because this broker still assumes, but some point of time it has to stop using that controller service, because it's just like a service. This controller, it actually is present in all brokers, but only it has to be initialized. And it has to run, because I think the service keeps on running always, but it only picks up that controller epoch value.
Yeah, it's about controller, yeah. And what will be done if just leader for particular partition will came back? So it's about controller, yeah. When something happens to controller, we elected new controller has been elected. But what about leader for each partition? Can we have split brain in case of partition leader?
Well, so the partitions are actually so this is split brain is only for the controllers, isn't it? So the partition assignment will actually be taken care of immediately. So because the partition, if a broker goes down, okay, so you are saying the partitions on the controller, isn't it?
No, let's say that broker 2 was not down, but it has some slowness, yeah, and cluster decided that it was down, broker 2, yeah, but but broker 2 was not down, it was just slowness, yeah,
okay.
yeah, GC pause or something like this. Okay, so controller elected new leader for particular partition, let's say broker 3, now a leader for partition 2, but after some timeout, broker 2
Comes back.
oh yeah, came again, yeah. What happens?
Yeah, see, I think, this is what my opinion is about. See, in this controller, if a broker is a controller, even if it goes down for a certain amount of time or a small amount of time, so what will happen? The cluster will be totally unreliable. It will be very unsafe and very fragile. So it has to elect a controller immediately, because there is no controller and the controller is doing a very active part. Okay, so it has to elect a controller. So whenever the second controller is elected, the first one is totally ignored. Even whatever the partitions they are distributed, and if even it is still rebalanced, it will still live with it, because you can rebalance the partition later, but you cannot lose a controller. If you lose a controller for small amount of time, and if it goes for longer time, so all your whole Kafka cluster will come down. So that is very important. So in that case, it doesn't bother about the rebalancing. So it will just go for the next controller is elected, and it will move ahead, and then it will try to do a rebalancing of the partitions if required. That is what I think.
Yes, thank you.
Yeah. So, okay, this was one. And now if we, this is the other thing about like the Kafka delivery semantics. So this is, we'll talk about what a delivery semantics is. So it is basically nothing but how Kafka guarantees a message delivery to its client. That is what it says. And so what does that mean is, whenever any client, like a producer, publishes a message, so Kafka brokers or the cluster, it needs to send an ACK, whatever the way it is, so the best way we send an ACK is very important. To first of all, to give a guarantee that the message has successfully reached a Kafka cluster, and then how it is handled in the Kafka cluster, and how it is responded back, that is also very important. So it looks very simple, but it is not that. In fact, they have divided that the guarantees in three. One is at most once, at least once, and exactly once. So in this case, at most once means whenever a message is it can lead to message being lost, or it can be re-delivered or duplicate, all that. That is what the definitions are. But if you imagine, it is different for the producers as well as the consumers. If you look this basic diagram over here, so what is shown over here is like it is a very, very high level diagram of these producers and messaging system. So this is our Kafka, which is a messaging system over here. So the producer actually interacts with the data source to get all the events, and these events are actually converted to message and stored in the message system. And the consumer actually, consumes all these messages, and then it will actually use these messages, store it to some other destination. So this is usually what happens in if we are using a data pipeline, right? So now what happens whenever a producer is publishing a message? So there might be some ways to handle that. If it sends a message to a messaging system, it expects something from the messaging system. In some cases, it would be like, just write a message, to the messaging system and forget it. So that is almost like a streaming. That is what I think. It's like asynchronous way of doing it. And so in that case, what happens? Whenever you write a message to a messaging system, you don't wait for any acknowledgement from the messaging system. So if you see like a video streaming, we really are not interested, or audio streaming, right? So because the frames keep coming, and then if there are some misses in the frames, because there are very advanced algorithms which can really make up with a certain amount of frame misses, right? So therefore that is, but here the speed is important, and therefore in such cases, the asynchronous way, so you will possibly have a data loss, but the latency will be low, and also you will have a very high throughput. Okay, so that is way some systems are they are good with that, and the asynchronous way works. But only the problem is you will have some data loss in that case. And the second way, or when they talk about at least once, in that case, what it means is, whenever a producer publishes a message, it waits for that message to be written at least to the leader's commit log. Okay, and when it is written successfully, written to a leader's commit log, it will respond back with an ACK. So that is what it means, at least once. So message won't be lost in this case, but the problem is whenever there is a leader crash, okay, just after the commit, so then your message, whatever has been written before it is replicated to the followers, will be lost, right? So you will still have a data loss, but it won't be that dangerous than the previous one, right? In this case, the asynchronous, you might have data losses to a large extent, but in this case, at least the data losses will be reduced to larger extent, but you will have slight hit on the latency because you still have to wait for certain amount of time to be written into the disk, because disk writing to a disk consumes some time, right? So therefore, but it is still more reliable than the async way. But both of these applications are different. The async way application may be like a streaming application, that is fine for it. But in this later committed way, you might need, in some scenarios, at least the message has to reach the broker to some extent. But if it fails in the cluster, it's fine, because we all know that Kafka clusters are very, very reliable. They actually store the data, and the availability and the durability is very high. So therefore, in some cases you can take the risk, and occasionally if there is a failure in the data loss, then still that is fine. So those applications can go with this sort of delivery semantics. And in the last is like the strongly committed. It means like it will wait for the whole quorum to get committed. So in this case, like if you have a leader, so usually message is published to the leader. It is written in the commits log of leader, and also it is replicated to the Insync replicas or those two, or whatever the follower based on the replication factor. And then only when it responds back from the followers, the leader will actually send act back to the producer. So that is a very high, what you say, strong consistency in this case, and you won't have a data loss, but the downside is you will have a high latency, and it might also have an impact on the high throughput. So these cases are important in some cases, like when we do some transaction based systems. If you have that, so then this is the way to go. So therefore it says all Kafka has all these ways to do it, and they are again configurable. That is why it is said it has availability also, but then also you can have a strong consistency, but the only thing is you will have some trade-offs to deal with. But you have all these options and all these features already available. So this was for the producer side. Okay, so now what happens on the consumer? So what happens is, any messaging system, the consumer will actually pull all the messages from the messaging system, the Kafka system, and then it will process them, write it to a destination. That is what the general scheme will be, isn't it? So now these also have three different ways. One is at most once. So here, if you auto commit to the Kafka buffer, so whenever you have consumed data from any of this partition, and that is auto committed, immediately it commits back to the Kafka broker, and the offset increases. So in this case, if you just imagine this is some pseudo code written over here. So if you have a consumer which is polling for 100 messages in the records, and then you start processing them, and you are inserting into some data lake, right? So each record at a time. But in this case, what happens is, whenever the consumer dies, right? So if the consumer dies, so again it will come back, that is fine. But before that, the consumer has already consumed so much messages from the Kafka broker, and the offset has already moved forward. So even if the consumer dies and comes back, so it will actually move to the new to the new offset, and in that case there will be a data loss, right? Because you have not completely saved the data into the destination. In this case is a data lake. But so whatever you are starting with the other messages, and that is the reason all the messages won't be available in the destination. So if you go with this at the most once, you will have a data loss. So that is what it talks about if we have an auto commit enabled for the consumer. And in other one is at least once. So what it says is, you commit to the broker after the messages are consumed. So that is the mistake what we are doing here. we were committing before even we were actually pushing the messages to the consumer destination, right? So in this case, again, if you look at the pseudocode, so also the auto commit is not enabled in this case. And then you have this Kafka consumer over here. It takes all the 100 records, and now it is writing the records one at a time. It is inserting, and when it is inserted, then only it commits to the consumer, saying that, okay, this particular record has been committed, and then you increase offset. Okay, so this is good. Okay, but what happens is if there is a failure during this session, okay, when it has inserted a record and it doesn't actually commit to the Kafka broker. So again, if the consumer comes back, so you will see that the offset has not increased. So there might be a data duplication, because it will again start from that particular offset, and it will pick up the same record which was already stored in this destination, and it will try to send a duplicate record. So there will be a duplication of records. So in some applications, if they can live with that, then it's fine. And the third one is exactly once. It is again about the transactional based system. So what it says is whenever you are actually inserting into a destination, you don't commit, so you commit both of these, you do atomic operation. And so this atomic operation can be done by transaction, or they talk about use a two-phase commit. So one phase commit will be insert data, and the second will be for updating the offset, So that is one way to do. So this will be a very strong consistency, and it will be, but it will have its own downside of latency, and then the throughput and all that. So if that is the way it is being discussed here, is Kafka is very flexible, very configurable, and it based on the demand and based on the requirement, you can configure it in different ways and achieve all possible ways, what are required. So you can have very high availability, as well as low latency, also high throughput, or you can have a very what you get strong consistency for this delivery semantics. So this is what is about the Kafka delivery semantics. Yeah. Any questions anyone wants to add to this?
So these commit are from both producer and consumer perspective, right?
Yeah.
Insert
so
data will be.
It will be separate for the producer, because whenever producer actually sends a message to a messaging queue system, then actually that messaging system will inform the producer and by an ACK, right? The acknowledgement. Same thing with the consumer also. When a consumer pulls the data from the messaging system, it will send an ACK to the messaging system.
Okay, this message.
Yeah. So there will be two ways and two different ACKs received from the producer. Messaging system sends to the producer, and the consumer actually sends to the messaging system in this case.
Yeah.
So this was one. And now here the last part in this case, they discuss about the characteristics of Kafka. So what are the characteristics of Kafka? So basically, one is about this storing messages, right? So whenever we know that producer publishes a message to a Kafka broker, it gets stored in one of the partitions. Usually it is a leader, and that is what the commit log it talks about. And this is sequentially stored in the disk. And the reason whenever it is stored into disk, we always think about disk storage is very slow and it will consume a lot of time and all that. But what has been discussed is they are taking advantage of the OS features, as well as also the way it is written to a disk. Because if you write into a disk in a sequential manner, then a random block access, because usually most of the data is written in blocks on a disk. And if we align all our messages in a sequence, and we just keep on appending it block wise, so that is much faster. It's like almost 1,000 times faster than the random block access. And that is why Kafka uses that way. Like it uses something they call it as a read ahead and write behind of those logical writes into a physical writes technique. So when these are the OS features what it uses, and therefore it is very optimized. So whenever we think about disk storage, we usually think it's going to take more time, but it is not that case. Even though they are commit logs, they happen very fast, and that is the reason we get a very good latency, and also we get a good high throughput because all the messages are actually stored in batches as well as they're compressed, you know. So and therefore they are compressed, or whatever the batch size what has been configured, it is most of the time configured based on the block size what we are going to store in a disk. And if we have that exact block size, so that way we don't have to split within the blocks also, and therefore it is actually more efficient way of storing. That is what actually talks about in one of the characteristics. Yeah, and then it talks about something called page cache. It says that modern OSs cache the disk in the free RAM, and this is called a page cache. Frankly, I didn't go in details, but if anyone has any input about that, you can actually just chime in. Okay. If not, then we have the second characteristics here is the retention policy. So we all know that Kafka retains all these records for a very long time, and it has different options. You can actually select based on the time, how much time you want to keep the record, maybe days, hours, or maybe even forever, you know. But if we say if it is forever, then it limits based on the number of whatever the storage limitation is based on the hardware resources. So that is a way of doing it. One is it can be actually this retention policy can be based on either it is a time-based limit, and or it can be size-based limit, you know. So you can just limit based on the size, or it calls something like a compaction also. So if you have always latest versions of record being stored, so the previous records you can delete based on some policy what you can define there. So this is what actually is about the record retention in Kafka. Then comes what is the client quota. So we know that the clients for a Kafka are the producers and consumers at least. So in that case, what will happen is if a producer is trying to produce huge amount of messages, then our Kafka cluster is able to consume. Okay, because usually every time a Kafka, even though it can consume all the messages, but it is designed or maybe configured in such a way that it has a limited number of brokers, and based on that you can consume a certain amount of messages only. So the producer, even if it publishes a huge number of messages and the Kafka is not able to do it, so it will set a limit, and that is what is a quota. So you have two quotas. One will be for the producers and for the clients also, and this quota will be assigned per client ID, right? So whenever so if so happens based on the design, it is the producer is supposed to only produce a maximum of 100 messages per second, and the Kafka can publish that many messages. It works fine, but immediately if for some reason it starts producing 1,000 messages per second, so in that case the quota will kick in. But when that happens, the producer is actually the Kafka cluster or doesn't respond to the producer for that message with an error response. It doesn't do that. It allows it to slightly cross the quota, but then it will slow its response. So it will actually slow the producer in a different way. So then it won't consume that many number of messages. So this is the way it will do, and same thing it will apply for the consumer side also. If the consumer is trying to actually consume more messages, so because whenever such thing happens, it is actually going to block the network resources, isn't it? So it will be a bottleneck for everyone, and eventually the whole system will be unstable. So that is why it will also, even on the consumer side, if it is trying to pull a lot of messages, and if the messages are not coming at that rate, so that might be a lot many requests are coming to the cluster from the consumer, and in that case it has to slow down those requests also. So that is why we have a client quota for the consumer side also, and that is again configurable based on the quota what we have. Yeah, and actually they talk about it's like a byte rate threshold quotas, and yeah, so like it's 100 Mbps per second or something, what some examples are given at this. Yeah, so so this was for the client quota. If anyone has anything, they can actually add over here. Okay, so then, yeah.
I think I have one question here. The
Mhm.
quota will be used when the Kafka is deployed in a kind of cloud architecture, right? So if that is shared between multiple clients, and then they could use quota to control how much they can actually utilize the Kafka cluster. Is that way they use the quota?
Well, I'm frankly, I'm not very sure, but it should be for any system, right? Because whenever we are actually, configuring a Kafka for our application, we have already configured and designed for a certain number of messages from the publishing side as well as for the subscribing side, right? So whether it is a cloud-based or not, I think that should apply for both, but I might be wrong. Because whenever we do it, we don't want to overload the queuing system, the data pipeline, isn't it? And at least if it does, then it will be very fragile because of network consuming more network resources. That is what I think. Yeah, but what you say, and if you have something about it, yeah, that may be possible also. But this is just my thoughts.
Okay, got it. Yeah, thanks.
Yeah. So now this is about the performance. So in this performance, what it talks about is, so it says that Kafka is really popular because of these performances. We all know it is high throughput, low latency. It can consume n number of messages and can be configured infinitely, almost like that, because obviously based on how much resources you have. If you have more resources, and that is why the scalability comes into picture. So if you are actually having a system which has supposed to be accepting all the messages from a publisher, so in that case you should be able to quickly scale. Okay, so that is the way Kafka can be done. So if your application demands that, so it scales. So it scales to any extent. So that is what it means, and it scales very fast and without any having burden on other resources on other systems. So that is what is the beauty of the Kafka. So the clusters can be expanded or shrinked also when they are operating, so you can add more number of brokers, and so it will still function even if there are outages. Okay. And also it talks about, we have this the topics are actually divided into partitions, and again the partitions can be again divided among themselves. So that, because each and every partition is limited not by the Kafka, but it is limited by the size of the disk or space which it is running on a broker. And if that exceeds, then how we can handle that is we can again divide the partitions into more partitions. So that is also possible, and that can also be done. I think it can be done automatically also, or it can be done manually. Okay, I'm not sure of the automatic side, but it can be surely done manually, and can be done in a running system also. That is what I think. Okay, so therefore it is very flexible, and that is some of the reasons why it is popular. And the second is the reliability, or the fault tolerance, because every time, so as we said, like whenever we have a partition, the partitions are also replicated. So these replications are done in different brokers, and it may be the broker may be in the same cluster, in the same rack, or maybe in different racks. So that way also it is handled. And if there is any failure on any broker, it is immediately reported to zookeeper, and the zookeeper take an action and all that stuff. So therefore it is very reliable, and the reliability aspect is also very much popular in this case. It doesn't miss any of these messages, or even if the brokers are down. And therefore this is also very important feature in terms of performance. The second is throughput. Throughput, yeah, sorry.
One question.
Mhm.
Say, do they have any kind of like a number of brokers? Say they have like 5 brokers, and then all of a sudden 2 brokers died.
Mhm.
So do they still support the client request? Or is there any case like they should have minimum number of these many brokers so that then only they can serve the client request? Is there any kind of that kind of
Well,
limitation on the Kafka?
yeah, so it again depends on how you are configuring, like, so if you are worried about the delivery semantics, right? So usually what happens is, if you have brokers which have like 5 brokers, as you said, and 3 of them die if you have only 2. So then what will happen is, every time when we do a replication of a partition, it is replicated. If the replication factor is 3, so you still have 2 followers, isn't it? But now if you say all the 3 brokers have gone down, so what will happen is, the 2 brokers whichever remaining will actually consume all the leaders of those partitions. So it is still possible, okay? But then if your delivery semantics is configured to be strongly consistent in what we discussed just now, so in that case it might have an hit. So frankly, I don't know how it is handled if you don't have that many number of what you
Quorum they
say,
might be said.
yeah, the quorum, right? The quorum goes down.
Mhm.
Because I think the Insync replica will be instead of 3, it will be only 2. So if still it's okay, because I think it looks only at the Insync replica at least, and then it says that it is fine. But what happens if we have only 2 broker and suddenly the second broker also fails? Okay, so then there might be a data loss, even if it's a transactional based system. So how that is handled, frankly, I don't know. But they claim these things happen, and they take care of it. But then I think, they might have some other way to address that issue. It just not on the single cluster in a single rack. It might be multiple racks and all that, and still that is the way it is more reliable. That is what I think.
So
Yeah. Mhm.
yeah, so what I thought is like because the zookeeper part, they're trying to move it to the Kafka cluster, right? So
Mhm.
maybe they also need the quorum, maybe, because earlier it was in zookeeper, they used to take care of the quorum.
Yeah.
But here now they moved to Kafka. Maybe I don't know. Will they follow the same quorum concept what they use in zookeeper here too?
No,
Yeah.
Kafka does not use notional of quorum. Yeah, Kafka use notional of Insync replica, and you can set up size of Insync replica per each topic. You can set up 2, 3, or as many as you want. Yeah, you just need to have enough broker to have full set of Insync replica.
Okay. Okay. So it is based on the number of brokers which a cluster can administer. Okay. Mhm. So if it has more brokers, it can add them. But like in case if the brokers goes down, and if you have a single broker, so it's not like a dynamo, right? So it will keep on saying that it is highly available.
Yeah, but you can set size of Insync replica to 1 per partition. Yeah, if it's per topic, if it's okay for us. Yeah, we can set any size which we want. Usually we set 2 or 3. Yeah, but we can also set to 1, and in this case, so everything depends on setup per partition. Yeah.
Oh, okay. Okay. Excellent.
It just doesn't, I mean, not only Insync replica, but also replication factor, right?
Yeah, so the replication factor itself decides the Insync replica at least, right? Yeah. So I think that is also configurable, and it might be automatically configured in case if you have lesser number of brokers. So, but you still have to address those messages, isn't it? So you have to store them somewhere. And the good part is whenever it's commits to a leader, it will get immediately stored in a personal storage, So therefore, the data loss is very less, because if you talk about, when they talk about this low latency, they say 99% of the time the data is read from a disk cache or a RAM. Only 0.001% it hits the disk, So that much reliability and everything is already inbuilt in Kafka. Yeah, so the system, the design, the way it is designed, it's really very robust. Yeah,
Fault
so,
tolerant and
right, yeah.
it's highly available also, right?
It is, yeah, yeah. So therefore, as Nick said, right, so even if a single Insync replica is there, it still keeps on, you just reduce the number of Insync replicas or the replication factor, And if we think in terms of quorum, yeah, then the quorum size also reduces automatically, something like that. Yeah. Yeah, that makes sense. Yeah. So the second throughput is the same thing. Like, what throughput means is you use consumer groups. Different consumer groups can actually be parallelized, and they can talk with multiple partitions on a topic. And therefore, you have a more number of messages consumed by different consumers. So there is a parallelization on the consumer's front also. And also, when we are storing messages from a producer to all these brokers, you actually store based on the batch sizes and the batches. So therefore, the throughput is really very well handled in this. And also, the messages are compressed from the producer side till the consumer side. They are not uncompressed in the broker at all. So they are just passed on, and they are uncompressed only at the consumer side. So that way, it takes care of a throughput and addresses the throughput issue. So you have a very huge throughput. Yeah.
One question here for the compression and encryption, right? I mean, the encryption point. So earlier we have talked about the compaction at the Kafka, log compaction.
Log
right?
compaction.
Yeah. So if the data is encrypted, then how do we do log compaction?
So actually, it's not encrypted. What they say is, whenever we get a messages, a single message is not compressed. All of the messages in a batch, they are compressed together, and then that whole batch, or whatever that compressed form, that whole message is sent to the cluster. When there's nothing done at the broker end, but whenever it actually passes to the consumer side will uncompress them. It's not encryption decryption here. So log compaction, you are talking about the one whenever we are writing to a hard disk, right, in a leader or a follower. So that log compaction is actually just committing a log, whatever the way it is received from the producer, it doesn't do anything. It just copies the same, because it's in binary format. That exactly that binary format, that whole binary, whatever that message is, just copied in that disk as is. It doesn't change or do any modification in that, because if it does any processing on that message, it is going to have a hit on the latency.
Will take time.
Yeah, so therefore they don't want to do it. They just want to append it. And also, if you don't append it, if you do processing and then you try to write, because you get a messages in batches, and huge batch, and if you try to do it message by message, and then you'll have to again combine them and then push it into a storage block, right? So you'll have to again assemble them. So there will be some sort of processing involved, and that they try to avoid. And that is why they actually get a very good throughput, because it's a block based copy. Yeah, this is my thoughts based on reading after all these things. But yeah, if anyone has different opinion, yeah, please actually they can chime in here.
So you're saying that I mean, yeah, go ahead.
So the encryption, I mean, even if there is encryption, it's totally on the producer side, not it doesn't, like Kafka itself doesn't care, right?
Right, doesn't care. Yeah, you can see that if it's an encrypted message what we get, so the producer will just do whatever it has to do, because that is the secret, has to be revealed only to the consumer, not in
to the whoever has that. Yeah.
Oh, okay. You're saying only the data may be encrypted, not the key. So that way the key based on key, they do compaction maybe later point of time. They don't care, they just overwrite it, right? At the time of when they do log compaction. That time they don't care whether the data is encrypted or not. They just have to overwrite, right? If the key is same.
Yeah, so if whatever the data you get in Kafka, it will be stored as is. So whatever, if you have an encryption done at the producer side and we have all those encryption keys, that should be passed on to the consumer some way, because usually it is done, right? If you have encryption done at the producer side, the consumer will always knows whatever the key encryption is. So it will always have that information. So the Kafka just take the message as is, and then actually it just passes back to the consumer, and the consumer does all the decryption part in that case.
Okay, and then you're saying one more thing, right? Like batches. So the batch is gonna come like for each partition based batches, or is it like batches is like everything combined can come to Kafka broker and they have to split into between the partition based on the key?
Yeah, okay, that's a good question. So whenever we get a batch of messages, and if we think, because then the whole batch has to go to a single partition, then only it makes sense, isn't it? So then what I think is, whenever we have a batch, and if we have different keys, because if it's a key based partition, okay, then it doesn't make sense. So then we'll have to have different batches. Okay. So even if the batch size is smaller, it might be fine, because that is the way the application will have to decide. But if we are doing a batching, and then the whole batch has to go to a partition, then only you will get a good throughput. So that way you will have to design the system, the producer.
But the thing is, there are like many producers, right? So how do they synchronize to create a batch? Is the batch based on the Kafka broker level?
Yeah, it's based on the producer. The batch will be at the producer side.
Oh, you mean for each producer, they have to take care of the batch and then send the batch to a particular partition at a time.
Right,
instead of sending one each.
Yeah.
Yeah.
But that will cause a latency.
So in the last
producer side, right?
Yeah, that might be. So therefore, they have that configuration, right? Either by the lag time, linger time, or the batch size. Yeah.
Batch size. Yeah.
Yeah, you have to wait for that many number of messages.
Oh, okay. Whichever is earlier, either the size or the time. Okay. Based on that,
the way you configure, yeah, because your application might demand different.
Yeah, right. Got it.
So, yeah, it was like a last call. In the last call itself, it's discussed.
Yep. Yeah. So this was it. Anything anyone wants to add? Shashank, you had something you were saying?
No. I was just listening, like that encryption part, what KK and Sri was talking about.
Yeah, I was also not knowing, but yeah, that's a good thing brought in. Cool. Okay, so then this was what I wanted to cover in Kafka, the last session. Okay, completed all that, but only that page cache, what they mentioned, I couldn't go in more details, but yeah, whenever we have some other session, we can discuss that. Okay.
Yeah.